FastMCP 2 employs dependency injection as its core mechanism for runtime context resolution, enabling tools to declare dependencies through type annotations or explicit dependency providers, without exposing these parameters to the client-facing schema. This inversion of control pattern decouples component configuration from execution while maintaining clean, client-oriented function signatures. We will examine how the framework initializes an MCP server instance and registers a tool that accesses HTTP request metadata through injected dependencies, demonstrating the seamless integration of runtime context into tool implementations.
From FastMCP, import FastMCP. From FastMCP dependencies, import current request. From Starlet, requests import request. MCP equals FastMCP demo. At MCP, tool. Async def client in forequest. Request equals current request, dict. Return. User agent, request headers get user agent, unknown. Client IP, request client host if request client else, unknown.
This code demonstrates FastMCP's dependency injection system for accessing HTTP request data in tools. The client info tool uses current request to automatically inject the Starlet request object, allowing access to headers and client information without exposing these as callable parameters to MCP clients. The pattern follows FastMCP's convention, where dependency parameters are excluded from the tool's schema, maintaining clean interfaces while providing runtime context. The implementation shows how FastMCP handles HTTP-specific dependencies gracefully. By using current request as a default parameter value, the tool can access request-specific data like user agent strings and client IPs, which are essential for logging, analytics, or security purposes. This approach is particularly useful in HTTP transports SSE or streamable HTTP, where request context is available, though it would raise a runtime error in non-HTTP contexts like SDDIO transport. The design choice to use dependency injection here keeps the tool's signature clean and focused on its core functionality. Clients calling this tool only see the return value structure, not the implementation details of how request data is accessed. This separation of concerns aligns with FastMCP's philosophy of hiding infrastructure dependencies from the protocol interface while making them available to tool implementations when needed. Let's break it down.
From FastMCP, import FastMCP.
Imports the FastMCP class from the FastMCP module, which provides the core functionality for implementing Model Context Protocol MCP servers. The imported class will be used to create MCP server instances with customizable identifiers.
From FastMCP dependencies, import current request.
Imports the current request class from the FastMCP dependencies module, providing access to request context information within the FastMCP framework.
From Starlet, requests import request.
Imports the request class from Starlet's requests module, providing functionality to handle and inspect incoming HTTP requests in web applications.
MCP equals FastMCP demo.
Creates an instance of FastMCP with the identifier demo. The string parameter serves as a server label for protocol handshakes, allowing clients to identify this specific MCP server instance during communication.
At MCP, tool.
Decorates the following function as an MCP tool, enabling FastMCP to automatically register it with the function name as the tool identifier, extract the docstring as the tool description, and generate an input schema from the function signature for parameter validation.
Async def client info request. Request equals current request dict.
Defines an asynchronous function named clientInfo that accepts an optional request parameter defaulting to the current request context. The function is declared to return a dictionary containing client information.
User agent. Request headers get user agent. Unknown.
Retrieves the user agent header from the HTTP request and assigns it to a dictionary key named user agent. If the header is missing, it defaults to the string unknown.
Client IP. Request client host if request client else unknown.
Extracts the client's IP address from the request object's client host property if the client exists. Otherwise assigns the string unknown to the client IP key. This is a conditional assignment that handles cases where the request might not have client information available. FastMCP2's dependency injection system elegantly bridges the gap between clean client interfaces and runtime context needs. The clientInfo tool demonstrates this by using current request to inject the starlet request object as a default parameter, keeping the tool's signature simple while accessing request metadata like headers and client IPs. This inversion of control pattern decouples configuration from execution, allowing tools to declare dependencies without exposing them in the client-facing schema. The design choice to use dependency injection here maintains FastMCP's philosophy of hiding infrastructure details from the protocol interface while making them available to tool implementations when needed. The result is a clean, focused tool interface that abstracts away the complexity of request context resolution, providing a seamless developer experience for both tool creators and clients.
The client reaches for its reflection, but get HTTP request hands it a request that was always holding the mirror.